Alright, so let's go over question 5 from fall 2017. The first question asks two true or false questions. The first one is true. A fully associative cache has no conflict misses, because in order to have conflict misses, you have to have an index. However, since fully associative caches do not have indices, they cannot have conflict misses. Therefore, the only two types of misses that a fully associative cache can have are capacity and compulsory misses. The second question asks whether or not a write-back cache must write immediately to memory when a block is modified, and that is indeed false. If a cache writes to memory immediately when a block is modified, that's a write-through cache, not a write-back cache. Write-back caches write to memory whenever they feel like it. Now let's look at part B. So part B asks for a TIO breakdown of this cache here. So let's first try and figure out what the offset is. So this cache, or the problem mentions that, let's see, how big is the block size? Okay, so it says the block size here is 2 word blocks. So because the word is 4 bytes, right? This means that the block is 8 bytes in total. We can apply the formula here and set the offset to be equal to log base 2 of 8, which would give us 3, or we can think about this intuitively. And again, draw out a block with 8 items. This first item here is at index 0, this last item here is at index 7, and you need 3 bytes to index off this, or 3 bits to index off this. Alright, now let's try to find out what the index is. So they give it to us here as well. There's 16 sets. This means that we have 16 different indices possible. So again, we can do a log base 16, log base 2 of 16, which would give us 4. And we can also think about this intuitively, where we can have a bunch of indices here. First one starts at 0, last one has a 15, and we need 4 bits to index off this. Now notice that this is a 16-way associative cache, which means that each of these sets has 16 blocks. Alright, now we got to figure out what a tag is. When I find a tag, we need to first figure out how many bits you need to add as the physical byte address space, and then subtract the I and O from it. So they give us the value here, 128 TB bytes. So 128 TB bytes is equal to 2 to the power 40 times 2 to the power 7. You get a 40 from the TB byte prefix, and you get 7 from 128. And I guess it's 2 to the power 47, which means that there are 47 bits in the address space. So T is equal to 47 minus I minus O, which is just equal to 40. Thus our TIO here is 40, 4, 3. Now, one thing that's important to note here is that we won't really be looking at all 40 bits of the tag. This is a huge number, but for the most part, it's mostly irrelevant. These two numbers here, plus the 16-way set associativeness, are a lot more important. Okay, so now let's look at part C. What is the hit rate for running the loop below part C using the cache from B? Okay, so now let's look at this code segment here. First of all, you can kind of ignore this part, ignore these numbers. I just focus on the axes. So if we were to draw them out sequentially, we get B0, A0, B1, A1, all the way up to B15, A15, B16, and A16. So one of the first things I do whenever I encounter a cache problem is I just write out all the memory axes in order. That way I don't worry about what's going on in a for loop necessarily. All I care about are the writes and the reads. So here, we first access B, then A, then B, then A, and B and A, B and A, and so on and so forth. So, the distance between B0 and B1 here is 4 bytes. And the distance between A0 and A1 here is also 4 bytes. If we recall, our block is 2 words. So this should be enough to store B0 and B1 within one block. This means in this first access here, we're going to have a compulsory miss. But when we have this compulsory miss, we also load in B1. And same here for A0. We also load in A1. Now, because this is a 16-way set associative cache, we don't have to worry about the fact that A0 might replace B0. We have enough space in this cache to be able to store B0 then B1, and then also A0 and A1. And since we only go from 0 to 16, we don't have to worry about going back to previous items. Yet. Therefore, we can safely say that the cache access pattern is a miss, miss, hit, hit, miss, miss, hit, hit, and so on and so forth. Thus, the hit rate for running the loop below part C is a 1/2.